Hola, Pilar.
Hello, sorry. I don't know what happened there. My connection with the cable was not proper.
I went on live on YouTube, so maybe it's this one to change the setting. So I think we can start. So welcome everybody to this third week of the Invisible School. This week will be the week of the neutrinos, and we have together, we have today Pilar Hernandez from Valencia. She's very big expert in neutrinos, and I think that she will come making presentation with the slides. So please, Pilar, go ahead.
So thank you. Let me, where is this slideshow? Play from start. Okay, so can you see my slides now?
Yes, we can.
So very good. Welcome everybody. I can see you. I hope you can see me. So we are going to talk about neutrinos this week. You might, you know, of course, that neutrinos are just one more particle in the families of the Standard Model. And not all particles will get a week of lectures. So you might wonder why we have a week of lectures on neutrinos. And the reason is twofold. On the first hand, the neutrinos are so weakly interacting and so light particles that the strategies to measure their properties and the experimental techniques required to produce and detect them are rather unique. Okay, so this is a whole field of research. And secondly, I would say that neutrinos have already demonstrated that they don't quite fit in the Standard Model as it was written originally by Weinberg, Glashow, and Salam, because they have masses, and these were not accounted for in the original model. So the model has to be extended, and actually it is an open question how this extension goes. So in fact, neutrinos could be hinting already at, the first solid hint of physics beyond the Standard Model. Strictly speaking, this is the case. So I hope I will cover all these aspects in these lectures. So my plan is the following. So today we will start slowly with an introduction, a review of how neutrinos came to be discovered and eventually became key in the construction of the Standard Model. And then we will discuss how we go about giving neutrinos a mass in the Standard Model while preserving gauge invariance, okay? And there are two options there. And they have, as we will see later on in the lectures, very different implications. But we will just review these two alternatives today. Tomorrow we will discuss neutrino oscillations, the phenomenon that has allowed us to actually learn all what we know about neutrino masses and mixins, and we will discuss this phenomenon both in vacuum and in matter. And then we will review all the experimental evidence that has been gathered for the last few decades on these neutrino properties. So the last two lectures will be devoted instead to looking at the future and so where we stand with what we know, how we fit all this data together, and what is still open questions to be known in the future, and what are the prospects therefore. And then we will come to discuss neutrinos and the connections, the possible connections between neutrinos and beyond Standard Model physics, in particular as regards other open problems in the Standard Model, for example, the matter-antimatter asymmetry that we observe in our universe. So that's the plan. So let's start with lecture 1 today. And as I say, I will start from the very beginning because I think there are some lessons in neutrino physics that are interesting to not forget about how science actually works. Okay. So as you might know, neutrinos made their appearance in the history of physics as a phantom or dark particle with the discovery of radioactivity at the beginning of the 20th century, in particular beta decay. So in the beta process, a nucleus undergoes a transition in which the atomic number is increased by 1, while the mass number remains unchanged, and apparently emitting only an electron. That's the only thing you observe. Now, because the nucleus, of course, is much heavier than the electron, both the parent and the daughter nuclei remain at rest approximately, and therefore energy conservation, energy momentum conservation in this process would tell us that the energy of the electron should be fixed simply by the difference of the rest mass energy of the father and daughter nuclei. So it should be constant, right? So for a few years, and a very famous physicist, I don't know how to put this somewhere else. I don't see half of my slides, but so measure the spectrum. So they counted how many electrons came out of this process at a given energy. What one should have observed is that according to this principle, energy momentum observation, is that the momentum, the energy or the momentum of this electron should be fixed, should be a peak, delta function around this Q value. But instead, what they observed was a continuous, let me put the laser pointer, they observed this continuous line, so the electron came out with any possible energy below that value. Okay, and it took a couple of decades to actually come up with an explanation of this process, and a great physicist like Pauli, he came up with an idea that he called desperate remedy to save this energy momentum conservation principle, which was that in the process, another particle was being emitted together with the electron. And therefore, these two particles, the sum of the energies of these two particles should be equal to this Q value, but not any of them, so they could distribute the energy among them. And that would explain, of course, this continuum spectrum. At the beginning, he proposed to call them neutrons. Okay, at the time, the neutron hadn't been discovered. And of course, he figured out what were the basic properties of this particle. It should have spin 1/2. It should be quite light to explain the spectrum. Soon after, the neutron was discovered, and so it was clear that whatever was in the nuclei to keep the nuclei together was not this phantom particle, and the name was changed to an Italian name. It was rebaptized as neutrino in honor of Enrico Fermi, because Enrico Fermi was among the first physicists to actually take seriously this desperate remedy of Pauli and actually constructed a theory out of it, the famous Fermi theory of the weak interactions, in which he imagined this process happening because of a four-fermion interaction of this form, where a neutron would become a proton after emitting an electron and a neutrino. At the time, there was no clear idea of whether it was a neutrino or an antineutrino. Okay, but then Fermi, of course, figured out that if that process was happening, the inverse process in which the neutrino would be in the initial state should also happen, and therefore the neutrino should interact with matter via these inverse processes as well. Now, this looked like a nice theory, it is fun to remember that the famous Nature journal did not publish this article. According to the referees, it contained speculations too remote from reality to be of interest to the reader. Of course, as you might imagine, these were good old times where papers had to be of interest to readers. And Bethe and Peirce, they used this fermion theory to estimate a neutrino cross-section. And they came up with this extremely tiny number. So the order of magnitude for neutrino energies of 2 MeV was 10 to the minus 44 centimeters square. Okay, so this it was really tiny. And they actually declared in that paper that there was no practically possible way of detecting a neutrino. And indeed, it is difficult, and you can estimate, for example, the mean free path of a neutrino in some medium by considering this with this energy, by considering this cross section and the number density of targets in the medium. The inverse of the number density times the cross section gives us something of the order of a length, the units of length, and this is the mean free path. So it would be the typical path that a neutrino has to travel before it actually has a probability of order 1 to interact, okay? So if you estimate, if you put the numbers there for the density of targets in water, for example, you come up with this huge 10 to the 3 light years, okay? So you would need a really large pool of water to actually stop with probability 1 a neutrino. With these facts, Pauli was famous for coining this sentence: I have done a terrible thing. I have postulated a particle that cannot be detected, okay? Nowadays, of course, most theorists, most phenomenologists are postulating particles that cannot be detected, so this is no longer a sin. But for Pauli, this was really bad, because Pauli was famous for considering that a theory must be falsifiable, okay? His worst insult for a theory was that if it was not even wrong, that it means it is not falsifiable, then this is not a theory, okay? So it is something to reflect on. Fortunately, Pauli was a theorist, and actually a theorist that was known because there was this tale that wherever he would get close to any experiment, the experiment failed, okay? That was the famous Pauli effect. But, you know, there were very courageous experimental physicists that thought about this, and actually it was just a question of time and ingenuity to detect Pauli's neutrino. Because if you want to beat any small cross-section, you know what you have to do, okay? If the probability of one neutrino to interact is really so small, then you should have many neutrinos and try many times. And you should also have as many targets as you can, okay? So first of all, you need a very large flux of neutrinos, and okay, but this was being developed. Nuclear reactors are such a huge flux of neutrinos. A typical nuclear reactor is producing about 10 to the 20 neutrinos per second isotropically, okay? So if you can, if you locate a detector at 100 meters from a nuclear reactor, you should be able to estimate relatively quickly with a few numbers what is the mass of that detector in order to get, let's say, a few events per day, okay? That's the exercise for you. This is one of the most common exercises in neutrino physics, so you should be able to do this. What mass of a detector made of for example, water, but it really doesn't matter too much, you would need to get a few events per day. Okay, so you can do that while you listen to me and give me the answer at the end of the lecture, maybe. So this is what these two gentlemen did in 1956, Reines and Cohen. They started the intriguing poltergeist project. It was called like that because they were after a phantom particle, okay? And the first idea they had was actually to locate a detector close to a nuclear explosion, which of course nuclear explosions would also be a very intense source of neutrinos. And they even thought it through and draw this nice diagram. Of course, after a while, they came to their senses and they realized that it would be much safer to actually do it near a nuclear reactor. And that's what they finally did. They locate their detector with a mass of the order of what you have to compute near a detector at Savannah River, and they actually discovered the antineutrino. In order to do this measurement, I mean, even if you have a few events per day in a relatively large detector, you need a very good background reduction. And this is what they got, okay? They had this strategy, this golden signal, to actually reduce the background sufficiently to actually observe this signal. So this is the inverse beta process in which an antineutrino, and at the time they didn't know what was being produced at a nuclear reactor, whether neutrinos or antineutrinos, but fortunately they were antineutrinos. So they would interact with a proton producing a neutron and a positron. The positron will travel and annihilate into two gammas. And then the neutron with delayed coincidence will travel a bit farther and get captured eventually and produce another signal. So these two signals in delayed coincidence was a very, very strong background reducing strategy, which is such a good idea that is actually still used today. So there are many modern versions of Reines and Cohen experiment. We have many nuclear reactors around the world, and there are many neutrino experiments still working today, looking at reactor neutrinos. These modern versions of Reines and Cohen experiment go under names like CHOS, Double SHO, Diabe, Reno, as we will see tomorrow. And they are still making discoveries today. Okay, so that Nobel Prize of '95 was very, very well justified. Now, soon after the neutrino was first observed, it was soon realized that neutrinos come in flavors, okay, in families. They're families of neutrinos. Now, the muon had been discovered earlier on in cosmic rays, and it took some time actually for physicists to understand what was this muon, okay? In particular, it's so close in mass to the pion that it took some time to actually separate the two. And then physicists realized that what was going on in cosmic rays was this decay, a pion going to a muon, and something, of course, not observed. But again, for the same reason as in beta decay, it was thought that another phantom particle was hiding there, okay? And it was also suspected that that neutrino was different to that in beta decay. Now, when going to these higher energies, so the energies in reactor neutrinos could be MeV, while here in this process, okay, the neutrino energies would be in the hundreds of MeVs if the decay is at rest, but if the pion is boosted, it would be significantly higher. And neutrino cross-sections in the Fermi theory grows with energy. So if the energy of the neutrino is smaller than the proton mass, or below 1 GeV, this neutrino cross-section, just by dimensionality, should grow like energy square, okay? So actually it's easier to make interact higher energy neutrinos. So it was experimentally not so bad. And there came the next brilliant idea in neutrino experimental physics. Lederman, Schwarz, and Steinberger, okay, they used the first recently invented proton accelerators, okay, to recreate what was happening in cosmic rays in the laboratory, okay? So the idea was you have a proton beam that you have accelerated in your accelerator. You hit a target here in this very small black thing. And then in that collision, many pions are produced, which, like in cosmic rays, they would decay to muons and neutrinos. Now you put a detector behind a very thick shield that is able to stop all charged particles, and only neutrinos can transverse. And then you wait and look for a neutrino interacting with your detector and producing a muon, okay? And if this neutrino would be different to that in beta decay, then you would expect only to see muons. If it would be the same, then you would expect maybe to see muons or electrons. So this is how these three gentlemen discovered the neutrino muon. They indeed observed the appearance of muons events and not electron events. And this was the first time that there was a clear evidence that these particles in the standard model, at the time there was a messy situation with hadrons, okay? But this was the first hint that actually there were families with an identity, the family an identifier, the flavor identifier that was distinguished or could distinguish these families, okay? Again, this was such a great idea that is still working today. And neutrino accelerator neutrino experiments have beams that are produced in the same, basically in the same manner as in this original experiment of Lederman, Schwarz, and Steinberger. So again, there are modern versions of this, which are called globally accelerator neutrino experiments, and they go under names like MINOS, Operati, 2K, Nova. They are essentially the same idea, with, of course, much more intense neutrino fluxes and much bigger and sophisticated detectors, but they are still making discoveries today, as we will see tomorrow. So, of course, in all these processes, neutrinos, the neutrino properties were being also searched for. And in particular, one of the most important neutrino properties is its mass, okay? So how one could get a hint of the mass of neutrinos? Well, you can look at the kinematical effects of the neutrino mass in all these beta processes. For example, the most stringent comes from tritium beta decay. So this is one of the beta decays. If you look at the endpoint, so you measure the energy of, or the momentum of this electron, and then you look at the endpoint of the spectrum. If neutrinos were massless, then you would see that it ends at the Q value. But if neutrinos have a mass, then just for kinematical reasons, there will be a distortion of the spectrum, and the endpoint energy will be lower, okay? Because you have to pay at the minimum amount of energy that neutrino has to carry is its rest mass, okay? So with this process and similar processes for muon and tau beta processes, you can set upper bounds on neutrino mass. And for a long time, until very recently, the limit coming from tritium was the strongest, and it's set as a limit on the neutrino electron mass, which is the one that is being emitted in this process, to be below around 2 electron volt by the Mainz and Troisk experiments. Similar, much worse limits come from other higher energy processes, such as pion decay or tau decays. So this is the reason that in the standard model, neutrinos were assumed massless, because there was just an upper limit on their mass, okay? Now, as I say, this has been recently reviewed. Let me put, let me just put my pen back. So this limit now has been very recently upgraded to around 1 electron volt. And this is by this Catherine experiment. Okay, sorry. So this is the spectrometer of the Catherine experiment. This is a nice photograph which shows how difficult neutrino physics, experimental neutrino physics is, even these days, okay? Their goal is to actually lower the limit on the neutrino electron mass to about, to improve it by at least 1 order of magnitude from the original number I told you, so below 0.2 electron volt or so. And they already had their first physics run to get this improved limit of about 1 electron volt. So this is an experiment that is still running and will run for a while until they get their goal sensitivity. Okay, so this is a very fast review on how neutrinos were discovered and came to be members, prominent members of the Standard Model. So you have had, of course, you have, I'm sure, courses on the Standard Model, and you got the first week lectures on the Standard Model. So now you are all very familiar with this table. Okay, so neutrinos, oops, what I did. So, oh God, what did I do? Great. Does it work now? No. Okay, great. Just a sec. Where is my cursor? There is no cursor. Okay. Okay, great. This is here. Okay. Probably it's my pen. I did something strange with it. Let's see. Okay. Okay. So neutrinos came to be the upper components of the lepton doublet. So as you know very well, the way these particles would interact and their properties are defined by the quantum numbers under the gauge group, which are written here in the notation of dimensionality of the SU3 representation, the dimensionality of the SU2 representation, and the hypercharge. Okay, so the lepton doublet means, this means that the lepton doublet is a singlet under SU3. This means that for all flavors, the lepton doublets remain the same under an SU3 transformation. They are doublets under SU2, which means that they transform in the fundamental representation of SU2. That means they transform with the Pauli matrices. And they have hypercharge minus 1/2, which means that under hypercharge gauge transformation, they simply transform like this, okay? Okay, so they have weak charges, but then what about electromagnetism? So as you know, the electromagnetic charge is given by the isospin plus hypercharge. So for neutrinos, which are the upper components of the doublet, sigma 3 is 1. Therefore, this is 1/2. The hypercharge is, as we have said, minus 1/2. And therefore, charge of neutrinos is, yes, 0. Okay? So neutrinos are the only fermions that carry no conserved gauge charge. Okay? And in that they are special. All the remaining particles in the standard model carry some conserved charge. They carry electromagnetic charge. Okay? And this will be important later on. Now, so the other important aspect of the standard model is this the left-right asymmetry of this table. As you know, because what we see is that particles on the left have different charges than the particles on the right. Most particles on the left have a counterpart on the right, except neutrinos. Okay. Now, what this left and right means, you all know. So we refer to left and right as chirality components. Okay, so of a Dirac fermion, and therefore they have either chirality, negative chirality, or positive chirality. And you know that these chirality projectors, when you take the relativistic limit, so the velocity goes to the velocity of light, they become helicity projectors. So they are projectors on helicity, positive or negative helicity. And I mean by helicity, of course, you remember helicity is the spin projection on the direction of momenta. So negative helicity means the spin is in the opposite direction to momentum. We call that particle left-handed. And when helicity is in the same direction, we call that particle right-handed. Okay. And as I say, neutrinos in this aspect of the standard model, this chiral property of the standard model, are special because they only appear on the left. They don't have a right-handed counterpart in the minimal standard model. Okay. So what does this mean? This means that all the remaining fermions, the one that have a left and a right counterpart, they are Dirac fermions. They combine into Dirac fermions, which is a 4-component spinor representation of the Lorentz group, which includes parity. Okay, so this is the minimal, the smallest dimensional representation, which includes for a spin 1/2 particle, that includes parity. Okay. And such an object represents or has 4 degrees of freedom, as depicted here. The red would be particle states, the blue would be antiparticle states, and you have both particle and antiparticle with either helicity. And you can see how parity and charge conjugation takes you from one state to the other. Okay. So if we consider the left and right projections of this Dirac fermion, they combine in this way. Okay, so the left-handed part would be the combination of a particle with negative helicity and an antiparticle with positive helicity, while the right-handed chirality would be the other 2 states. Okay. Instead, a neutrino is not a Dirac fermion, it's a Weil fermion. It's a 2-component spinor, which is the minimal spin 1/2 representation of the Lorentz group for a spin 1/2 particle, which does not include parity, okay? So it only gets these two states, particle with negative velocity and antiparticle with positive velocity, and therefore it breaks both charge conjugation and parity in the maximal possible way, okay? Okay, so we said that the quantum numbers of neutrinos determine how they interact, and we have seen that they don't have electromagnetic charge, but they have weak charges, and therefore they couple both to the charge currents and the neutral currents. In the standard models, therefore the Fermi interaction is just when we look at it with a magnifying glass, which means we look at it at high enough energies, what we see it's coming from the exchange of a W boson. And similarly, there are neutral current processes, which were discovered later, which involve the exchange of a Z boson, okay? Now, these neutral current processes were very important in LEP era. So LEP was the predecessor accelerator at CERN of LHC, and this was an E plus E minus collider. And in these E plus E minus collisions that were tuned to have the energy of the Z mass, and therefore they were at the beginning in the first stage of LEP was producing very many sets because it's Z-T resonance. And then this set could produce all particle pairs in the standard model, including neutrinos, okay? So this was a very important measurement because it actually gave us a limit of what the number or a measurement of what are the number of families in the standard model, okay? Of course, you don't observe neutrinos in these LEP experiments. Neutrinos just go undetected, but you can do two measurements. You can, on the one hand, map this resonance of the Z boson, and from the width of that resonance, you can measure the total width, okay, which includes the possibility that it decays to neutrino pairs. And on the other hand, you can measure the exclusive channels to the different visible exclusive channels, one by one, to quarks, to leptons, and so on. And then you can take the difference between these two numbers, and this is what we call the invisible width of the Z boson. And then you expect this invisible width is coming precisely from the number of the events in which neutrinos are produced. And we know what is the width associated to one of these neutrinos. This is what I write here in the denominator. Sorry, I forgot I have the laser. So this is the width of the set going to one neutrino species. And if we divide the invisible width measured by the expected value of the width to one neutrino species, we found this number, which is 3 with very good accuracy, okay? Note that at the time there was a 2 sigma discrepancy, and this today would be a major thing. It wasn't for a long time, but actually this number has been recently revisited by some by theorists and experimentalists together. And now the number, after measuring an improved determination of Baba scattering cross-section and a reanalysis of the data in face of that, this number has now changed to 2.9963 with an error of 74, okay? So even the 2 sigma tension has disappeared, which is nice, before some theories tries to make a crazy model out of this, okay? Very good. So I hope I have convinced you that actually, even though neutrinos are the most elusive particles of the standard model, they have been key in the discovery of the weak interactions and in establishing actually the two most intriguing features of the standard model, which is this threefold repetition of family structures. Neutrinos allowed us to know that there are actually three families, and also the chiral nature of the weak interactions, because they are nowhere so obvious than in the case of neutrinos, which actually don't have a parity counterpart. Okay. Very good. So this is my short story of neutrinos in the standard model. Let's go on, because as soon as neutrinos, or as soon as neutrinos were discovered also from the very beginning, we realized that we are surrounded by an enormous amount of neutrinos coming from very different sources. Okay. And if you open your hand right now, you will be receiving about 5 to 10 to the 12 neutrinos per second coming from the sun. There are also processes going on in the atmosphere where cosmic rays impinge off the upper layers of the atmosphere, and they produce a shower of hadrons that decay to neutrinos. So you will be receiving about 20 neutrinos per second of those neutrinos. They are very different energies, so even though the number is much smaller, as we will see, they are very relevant. From the Earth itself is a very intense source of neutrinos. We'll be receiving about 10 to the 9 neutrinos per second. And this is from natural radioactivity. And we have also observed neutrinos from very, very far away in the universe. So the famous supernova 87 produce, if it happened, if we would be receiving now the neutrinos of that supernova, you will be getting about 10 to the 12 neutrinos per second. This is amazing, because this is more or less the same neutrino flux you get from the sun, except the supernova happened 168,000 light years away from us. Okay, so this is an impressive source of neutrinos. There are also relic neutrinos, like there are relic photons from the Big Bang, the famous cosmic microwave radiation. There is a relic of neutrinos out there. There are very many of them, again, in the same order of magnitude. They are very, very low energy, and therefore very hard to detect, and they haven't been detected yet. But I'm a theorist, but I would not dare to say that this is impossible, although it looks quite difficult. And recently we have got the highest energy observed neutrino events coming from outside the Earth or the atmosphere. These were observed by the ice cube detector in Antarctica. These were penta-electron volt neutrinos. The source of these neutrinos are still unknown, but clearly they come for very many extreme processes going on in the universe. Okay, so this is a very exciting new field that is still in its beginning. Okay. So we have measured many of these sources, not only those, but also others man-made. And in the last 2 decades, many revolutionary neutrino experiments have actually demonstrated that neutrinos are not quite the standard model particles that were conceived at the beginning, because they do have mass, they have a tiny mass, and massive neutrinos do require to extend the standard model. So let's, in the rest of this lecture, I will try to see how this goes about. Okay. So as you know, the Nobel Prize in 2015 was given to Professor Kajita, who has been a long-term member of our network in the Tokyo node, and Arthur McDonald from the SNOW experiment. And the prize was given for the discovery of neutrino oscillations, which we will discuss tomorrow, which show that neutrinos have mass. Okay. So tomorrow we will discuss all these evidences and the phenomenon of neutrino oscillation in detail. Let's just take for granted that all these experiments are correct, and we have and neutrinos have a mass. Okay. So how do we go about this? Okay, so you all know how a mass looks like in the Lagrangian of a Dirac. Let's first consider the case of free fermions. So let's forget about the interactions in the standard model for a second. You all have seen the Dirac Lagrangian describing just a massive Dirac fermion. And you know that the mass term appears in the Lagrangian like a term which looks like this, okay? If we separate the chiral components of this fermion field, okay, so we write psi as psi left plus psi right, what we find is that this term, and if you haven't done this, do the gamma algebra to see that actually only two terms survive here, which actually connect opposite chiralities. Okay. So this means that if I have a neutrino, which I just told you only has left chirality, then I cannot simply write this term, okay? Now, what this says is that the mass of a Dirac fermion I can think of as some interaction that is exchanging. If I do the Feynman diagram for this mass insertion, it's just an interaction that exchanges a right-handed into a left-handed or vice versa. Okay, and therefore, when a Dirac fermion propagates, is not left or a right state. Is really the combination of a left and a right. Okay, so a Dirac fermion is a superposition of necessarily the two chiralities. In the limit of high velocities is the same thing as the two helicities. So we have a problem to do this for neutrinos because we don't have the other helicity or the other chirality, okay? Now, is that the only thing we can do? Well, no, it's not. And the way out of this was thought of a long time ago by a very great physicist that unfortunately disappeared when he was very young, Majorana. He actually figured out that you can actually give a mass to a fermionic state, which is in a Weyl representation, okay? So how do you do that? Well, he figured out how to do this. So the Majorana mass term would be a term in the Lagrangian of the form m halves phi c bar phi plus phi c. And what is this phi c? The charge conjugated psi is just this combination, okay? So it's psi bar transpose times charge conjugation matrix, which is just combination of the Dirac gamma matrices, okay? And it turns out that if you now figure out, if you do the same and assume that you have just, for example, one chirality only, you find that actually this thing here, well, you can write this down a little bit more, and you find that you can rewrite this as psi transpose C pi plus HC. Okay, and this C matrix, you can easily check that it actually couples the same chirality. So I can write here left-handed, and this would not vanish, okay? What is the issue here? Well, the issue here is that in the same way that I can think of a mass term as an interaction that exchanges chirality, okay, I can think of a Majorana mass insertion as something that changes from nu left into the charge conjugated nu left, okay? But charge conjugation is also changing particle to antiparticle. This is why when a Majorana fermion is propagating, it's neither a particle or an antiparticle. It's a superposition of both, okay? In the same, exactly the same way as Dirac fermion is a superposition of the left and the right chiralities, okay? Now, of course, you have to convince yourself that this is actually allowed, okay? How do you convince yourself that this is actually an allowed interaction? Well, first of all, you have to show its Lorentz invariant. You have to show this thing by working out what this C matrix is that actually couples one chirality, so it's not vanishing for one chirality. It exists for just one chirality, and then you should check that the equation of motion coming out from this Lagrangian actually describes a massive particle. Okay, so these are three, of course, requirements to prove that actually this Majorana fermion is an allowed interaction. I can write down, okay, and it represents really a massive particle. And this is an exercise for you to do, okay, to think about and probably discuss on the Friday session. Okay, very good. So these are two options, okay? Now, what happens if we add the interactions that we have in the standard model? So you know very well that, of course, this is not something you write down in the standard model Lagrangian, because you know very well that left and right states for all particles, even if they have a right-handed state, they don't carry the same gauge charges as we saw in that table. And therefore, we cannot couple the two, maintaining gauge invariance. This is not allowed by gauge invariance, okay? What about the Majorana fermion? Well, this is even worse, okay? If you have an interaction of this form and you do any phase change of the fermion field, clearly this will not be invariant. Whether this phase is local, so it changes at each point in space differently, or is global, this will not be invariant, okay? So that term breaks everything, gauge, global symmetries, whatever, okay? So, of course, we have spontaneous symmetry breaking in the standard model. So we have the Higgs field, okay, which takes an expectation value, is a doublet, okay, and it gets an expectation value. And this is how we come around giving mass to fermions in the standard model. So can we do that for neutrinos as well in both directions, okay? If we know that we have spontaneous symmetry breaking, can I write down something that looks like a Dirac mass for neutrinos or a Majorana mass for neutrinos. Okay. So let's start with the massive Dirac neutrino. Okay. If we want to give neutrinos a Dirac mass, first of all, we need to have the right chirality. That it's clear. Okay. But if we have, so we have to extend the standard model, let's say with 3 right-handed neutrinos, 1 for each generation. And that allows me to write a Yukawa coupling, just like I do for the remaining fermions of the standard model. I can write, and now I'm going to write the generation index as well, because the coupling here could be generation dependent. Then I have my Higgs doublet, and then I have my right-handed neutrino. Okay, I can write that just like I do for the remaining fermions of the standard model. What is this phi tilde? Is just sigma 2 phi, or I guess there is an I in front. Okay, so that you can check that this phi tilde transforms like a singlet under SU3, a doublet under SU2, and it also has hypercharge -1/2, just like the lepton doublet has. Okay, and the expectation value of this field is V over square root of 2 over 0. Okay, so this means that first of all that I can couple phi tilde with L bar, just because the phi tilde and L have the same quantum numbers, and therefore if I take a dagger on the L, I get a singlet out of this combination. Which means that L bar and phi tilde are transformed. So this thing transforms like 1 singlet under SU3, singlet under SU2, and has hypercharge 0. So it's a full singlet, which means that the right-handed neutrino must have exactly the same, must also be a singlet. Okay. But if I have this, then I can generate massive neutrinos just by spontaneous symmetry breaking. Okay, the fact that this field has an expectation value, it means that this term results in a term like this. And of course, this is the index of the right-handed neutrino. So, so this Yukawa coupling, which looks like an interaction with a single field like that, okay, induces a neutrino mass of the form Yukawa times Bev of the Higgs over square root of 2, okay? And then neutrinos get a mass just like any other fermion in the standard model, okay? So that's exactly what I wrote before. What about the massive Majorana neutrino? Can I build a Majorana mass using spontaneous symmetry breaking? Okay. So here, well, I just said that L bar phi tilde is a singlet, okay? And this is also a fermionic object because the lepton doublet is a fermion and this is a scalar, spin 0 scalars, and therefore this object here is fermionic. So I can write a coupling, what we call a Weinberg interaction, because Weinberg was the first to write this interaction of the following form. I can just do the same thing that I do if I had a singlet fermion to write a Majorana contraction, okay? So remember that I could write a Majorana contraction by taking this, and then this was C, the matrix C, and then I take phi, so the transpose of this thing here. Okay, since this is a singlet and this is a singlet, this whole thing is a singlet, so it's perfectly fine for gauge invariance. And then the question is what happens with this operator when I take into account that the field phi gets an expectation value. Okay, so this term actually becomes alpha ij neutrino left. Remember, I only have left-handed neutrinos in this case. I didn't add anything to the standard model. And then you get V squared because you have two insertion of the Higgs field over 2. And you have another left-handed field and of course a charge conjugated matrix. Okay. Plus the complex conjugate. And this is indeed the Majorana mass insertion with a Majorana mass which could be alpha V squared, alpha V squared basically, because the 2 is there for a Majorana fermion. So, using spontaneous symmetry breaking, I can also give neutrinos a mass in this way. Now, this interaction with the Higgs looks different to the usual one for the remaining particles of the standard model because it requires 2 Higgs insertions, okay? And then by dimensional analysis, we know that since of course, the dimensions of the neutrino mass is 1, okay? Then, and the dimension of V squared is 2, this means that the mass dimension of this coupling must be -1. So this means that alpha must be some adimensional coupling divided by some scale. So this is an energy scale, which could be different. I mean, could be a new different scale to any other scale in the standard model. Okay, so this is a new physics scale. Sorry, I cannot write very well with this pen. And in principle, it could be unrelated to the only scale we know in the standard model, which is that of the Higgs mass. Okay.
Pilar, one question. Is phi tilde defined? Okay, the student thinks that the definition of phi tilde is different from a previous slide, and is asking if it is...
Yes, sorry. This was, of course, my wrong. I didn't have it in front of me, and therefore I did it wrong. Of course, otherwise you wouldn't get. So this should be out, and this is sigma 2 phi star. Okay. Otherwise, you wouldn't get this charge. Okay.
Okay.
Nice. Thank you for being listening. Okay. So. So this means that the coupling in this case should have, as I say, mass dimension, and that this dimension, this energy scale, could be different to anything we know in the standard model. So this brings us a little bit back to Fermi times. Okay, if you remember, before the standard model was invented, there was this situation where there was this beta process which could be explained in terms of this Fermi theory, which involved an interaction of this form, a 4-fermion interaction. You can easily check that the dimension of the coupling in that interaction must be -2, okay, which means that it must be given in terms of some adimensional coupling over a scale to the power 2, okay. And indeed, we understood when the standard model was discovered that the scale was given by the mass of the W, which was the particle that was being exchanged in order to create this four fermion interaction, okay? So we are a little bit in the same situation nowadays. If we go and give neutrinos a mass without enlarging the standard model and adding right-handed neutrinos, we give them a mass with an interaction, the Weinberg interaction, then we expect that the scale lambda that appears in this coupling is related to new particles, okay, that are being exchanged in this interaction. And we haven't observed because we are at energies where we cannot really tell what's going on at these very short distances, okay? So in this line of thought, there could be a neutrino, a new standard model, which incorporates neutrino masses and will bring in all these new degrees of freedom that are responsible for this Weinberg interaction. Okay, so this is of course very interesting. Now notice that this also means that the higher we make this high energy scale, the higher we make the mass of these extra degrees of freedom, the lighter neutrinos will become. So this is the famous seesaw mechanism, okay? Neutrino masses, if they are Majorana, if they come from this Majorana interaction, they are inversely proportional to some high energy scale, and if this high energy scale is arbitrarily large, then neutrinos are arbitrarily light, okay? And this is of course very welcome because we have also this situation that if we plot the fermion masses of all particles in the standard model, we find of course the flavor puzzle. There are many orders of magnitude where quarks and leptons spread, but there is an even bigger gap with the masses of all these particles and those of neutrinos. So if neutrinos would be getting a mass in this slightly different way, then we would have an explanation, a natural explanation of why neutrinos are lighter than the remaining particles, simply because the masses of the other particles that are charged, okay, they are proportional to the wave of the Higgs via Yukawa coupling, while the neutrino masses are basically a dimensional coupling, just like the Yukawa coupling, but then times the Bev square over some high energy scale, okay? And therefore, if there is a hierarchy in those scales, then there is a hierarchy automatically in neutrino masses, okay? So this is of course very interesting, and it will be the subject of the last lecture. Okay, so we will come back to this of course, because this is extremely interesting. But for the time being, let's look at the phenomenology, and the most important implication of neutrino masses is that neutrinos also mix, okay? They mix less than quarks because the neutrino masses are so light, but they actually, the lepton sector becomes just as complex as the quark sector in the standard model, okay? So how this goes around, you had all the last week, you had a whole lecture on flavor, so this is very similar, so I will go a bit fast here. As I said, all these Yukawa couplings we have been writing both in the Dirac interaction and the Weinberg interaction. They are completely generic in flavor space. They can link families, and therefore, let's consider first the Dirac case. So in the Dirac case, the fermion masses are just completely general complex matrices in flavor or family space. In the case of neutrinos, we have an extra one that we didn't have before in the original standard model. Now we can take any complex matrix to a diagonal form by performing a unitary transformation, which on the left and an independent one on the right, okay? So for all, we can do this for any complex matrix. So we can now go to the mass spaces by performing this unitary rotation on the fields. Okay, and it turns out that all of them disappear, okay, or these rotations disappear from the Lagrangian, except in the charge current interaction term. Okay, so in the charge current interaction term, two of these matrices in the lepton sector survive, which is the one on the left for the leptons and the one on the left for the neutrinos. And since these two matrices are not the same in general, then this product will remain. And this is what we call the PMNS matrix after Pontecorvo, Masaka, Nakagawa, and Sakata, and is completely analogous to the CKM matrix in the quark sector. Okay, you have seen that in the quark sector, this matrix, which is a generic unitary matrix, depends on three Euler angles, like any three-dimensional unitary matrix. But general unitary matrix, in principle, depends on could depend on 6 phases, okay, CP phases or imaginary phases. While most of them can be reabsorbed by field redefinitions, which can absorb many of these phases, to leave only one physical phase behind. Okay, so this is completely the same, fully identical in the quarks in the lepton sector now. Okay, so if neutrinos get a Dirac mass, then the lepton sector looks very, very similar to the quark sector. And there is in principle a phase in this matrix, which is physical. Now, what happens if we do the same for Majorana fermions? So we use the Weinberg insertion instead. We don't extend the standard model with right-handed neutrinos. We just give them a mass using the Weinberg interaction. Well, the situation is very similar. The only difference is that now these matrices, okay, which have a Majorana structure, necessarily are symmetric matrices. Okay, so the transpose is the same as the matrix, and this is because if the matrix could have any non-symmetric part, it will disappear. It will cancel when we do the complex conjugate. Okay, so the complex conjugate term will cancel any of that. Okay, now of course we don't have right-handed neutrinos, but fortunately, when you have a generic complex symmetric matrix, you can take to diagonal form with a unitary rotation, which is the same on the left and on the right. Okay, only with a transpose. Okay, so this is of course necessary because what we have on the two sides of this matrix is the same field. So we better do the same transformation. Otherwise, we would not be able to get to a diagonal form to the mass metric, to the mass eigenbasis. Now, if you do that, again, the only place where these transformations do not disappear is the charge current interaction, and is exactly the same as in the previous case. Okay, you get the product of the transformation you have to do on the neutrino fields, and the transformation you have to do on the left part of the lepton fields. Okay. So the only difference here is that actually you cannot reabsorb so many phases as in the previous case, okay? So because you don't have the right-handed neutrinos, you don't have so much freedom to absorb these phases, and in the end, you end up with a mixing matrix that has 3 physical phases, in principle measurable phases, okay? Now, the third exercise for you today is to make sure you agree with this statement that there are 3 physical phases when you have a Lagrangian of this form, okay? So I guess you did some of this last week of how you count physical phases. So I hope you can repeat the exercise for this new Majorana term to make sure you agree with this statement. And if you have any problems, you can ask, and we can, if you're interested, we can discuss that all together tomorrow, but I think it's relatively easy, okay? So, so the final conclusion is that if we look at the weak interactions, okay, So if we think of the weak interactions in the mass basis, so here we have the mass eigenstates, neutrinos with a well-defined mass, and leptons with a well-defined mass. The matrix here is the basis PMNS matrix. So we can either work in this basis, or we can work in what we call the flavor basis for neutrinos, which is just the product of this UPMNS matrix with the mass eigenstates, okay? This combination here. And this is what we call flavor basis, simply because what comes out of that product would be the states that actually couple with the mass eigenstates of the leptons, which are the electron, the muon, and the tau, okay? The usual parametrization of this mixing matrix is written here. So it's the product of 3 2x2 rotation matrices with the basically Euler angles. One of the phases appears as in the case of Dirac neutrinos, like a Dirac phase, and then the Majorana, these extra Majorana phases that are there only if neutrinos and Majorana, they are written as an extra matrix of phases on the right, okay? Very good. So this will be essential for tomorrow's lecture when we will be discussing neutrino oscillations, okay? So it is obvious that the question of whether neutrinos are Majorana or Dirac is a key question, and we don't have an answer to that question. So let's reflect a bit on how, what it will take to actually tell whether you are in one or the other. So imagine, in principle, the experimental signature could be, in principle, very clear. Imagine that you have created a neutrino beam of neutrino muons from pion decays, like I showed you from accelerators. So you have a proton beam hitting a target producing pions. You can, with a horn, I mean, you can focus the positive pions, for example, getting rid of the negative ones, and then you let them decay, and they will produce essentially a beam of neutrino muons, okay? And now you intercept this neutrino muon beam with a detector, and then you can have a situation where, of course, a neutrino muon, if you have Dirac neutrinos, they can only produce muon, negative muons, okay, in the detector when they interact, okay? However, if, because as I said, a Majorana fermion is both a particle and an antiparticle, it actually, if the neutrino is Majorana, then it can interact in the detector and produce both a negative muon and a wrong sign muon, a positive muon. Okay, so this looks like a very clear signature, right? If you do this experiment and look at and find wrong sign muons, you know that your beam is made of neutrino muons, so they should only produce negative muons. If you find a positive muon, there you go, you have a Majorana neutrino. Okay, in principle, this is true. In practice, this is very difficult. Why? Because the probability of this process is tiny. Okay, if you look at the rate of the wrong side muon versus the right side muon, it is suppressed by a factor which is typically the neutrino mass over the typical energy energy of the process squared. Okay, and neutrino masses are very tiny, as we have seen, and therefore this is very difficult. Okay, the best, most promising avenue to measure this is looking for a very rare process, which is called neutrino-less double beta decay. We have talked about beta decay at the beginning of this talk. Many nuclei undergo beta decay, radioactive nuclei undergo beta decay, but in some cases this is forbidden because the daughter nuclei is heavier than the parent one, for example, and then the process cannot is forbidden. However, the double process, or a double beta decay, is allowed, okay, by energetic considerations, and therefore you would expect to have of course, this process is very, very suppressed. It's a double weak process, so it is suppressed. But if you have a good enough experiment, you might hope to see it. And now, in the usual way, this process goes producing 2 electrons, like in beta decay, single beta decay, you produce 1 electron and 1 antineutrino. In double beta decay, you produce 2 electrons and 2 antineutrinos, okay? However, if neutrinos are Majorana, then again, the antineutrino produced in one of the processes can be absorbed in the second process, and then the neutrino can be virtually exchanged between the two, and this generates a process in which only you produce a double beta, but without neutrinos in the final state. So again, we go back to a situation with all the energy of this decay to be given, I mean, by the sum of the energy of the 2 electrons. So we are back to a situation where our expected signal for that process would be a peak at the Q value for this process if you sum up the energy of the 2 electrons, okay? Now, if you compare, so I should say that this double process, even though it's very rare, has been measured for several isotopes, and it ranges in the range of 10 to the 18 to 10 to the 21 years. So it's a very, very rare process. That's the lifetime. Now, if you look at the neutrinoless process, then you find, first of all, that there is some enhancement of this over that because of phase space. You have 2 particles in the final state here as opposed to 4. So there is a huge enhancement of the neutrinoless part by phase space. But then you have, as I said, completely generically, any process that would would look at the Majorana nature of neutrinos will have this suppression. Okay, so this is a big suppression, and we don't know how big it is because we don't have a measure of the neutrino mass yet. But this is the best hope we have, and in fact, this is a very, very active field where many experiments are trying to push the limit on the lifetime of this neutrinoless process. And so in order to estimate what is the expectation, and we will come back a little bit more to this on the 3rd lecture, so you cannot really understand what's here yet, but it depends on some properties of the neutrino mass, which is written here. It depends on nuclear matrix elements, and this is a very difficult quantity to estimate, okay? And then there is a phase space, which is easy to estimate, okay? So when you measure this lifetime, you're measuring the whole thing. So if you want your fundamental parameters, you need to also control quite well these nuclear matrix elements, okay? So this is why these ranges are rather large. So when people measure or try to measure this, and they don't find it, they set a bound on this neutrino mass parameter, but there is a large uncertainty coming from these nuclear matrix elements, okay? So, so I just highlight some of the most recent measurements, which, as you can see, are very recent. So there are many measurements in 2019. This is from the particle data book, and from 2018, 2016. And I highlighted the most stringent limits right now, which come from Gerda experiment, which uses germanium isotope, and Kamlan-Sen, which uses xenon 136 isotope, okay? And the prospects in this field are very promising. Many experiments are trying to push at least by an order of magnitude more the sensitivity limit, and we'll see the implications of that in the following lectures. So what about global symmetries? Of course, I said that if you have, I mean, there is a big difference in the 2 ways of giving neutrinos a Mars, Dirac or Majorana, as regards global symmetries as well. We have been discussing only gauge symmetries, but there are also some global symmetries at the classical level in the standard model, and even at the quantum level, right? So in the case of Dirac neutrinos, as soon as you at masses that are mixed families, you don't conserve any longer electron, muon, and tau number, but you conserve total lepton number. Okay, this means that if you rotate all the lepton doublets of all three families by the same phase, and you do the same for the right-handed leptons and the right-handed neutrinos, then the standard model Lagrangian with massive neutrinos is symmetric under that transformation. This means that the lepton number is conserved. The number of leptons minus the number of antileptons, not thinking about whether they are one flavor or the other, counting all of them, is a conserved quantity in every reaction in the standard model. Okay? Of course, there are Sphaleron processes that will break this symmetry, but we are not going to discuss this as yet. Okay. However, I said that Majorana neutrinos, the Majorana coupling, will violate any symmetry whatsoever. So we are not allowed, in the case of Majorana, the Majorana contraction, to rotate the left-handed doublet. Okay, because it will remain in the Majorana mass term. Okay, so Majorana neutrinos violate this global symmetry. Okay, there is no reason to a priori to believe that this global symmetry in the standard model is apparently an accidental symmetry, and we don't need to impose this global symmetry. But in practice, this would be an interesting new ingredient in the standard model, as it will bring in a new mechanism that could help us to explain the asymmetry between matter and antimatter in the universe, and we will be discussing more of this in the last lecture. Okay, so I think I'm done for the day. So it's almost 11:30, and I think it's long enough. I don't know if there are any questions or.
Yeah, thanks a lot, Pilar. If there are any questions, please write them down, and I will bring them to Pilar. Yeah, they're asking if the slides can be uploaded in the school website. So in case.
Yeah, I will upload them. Yes.
Okay, so just send them to me, and I will upload them to the website.
Okay.
Just a feedback. Can we move a little bit? Okay, can we move a little slower tomorrow?
Slower? Okay, I will try. I will try.
The speed of the slide, probably.
Yeah. I'm sorry. I try to slow myself down a bit, but I should slow a bit more. I mean, it's not fun to write on the pad, but and I'm not used to it, but I will do my best.
And it's also difficult having a feedback with the virtual lectures. So in case this is more for the students, just interrupt if you don't have something clear, just interrupt more and just make questions.
I think that's a good point. I mean, if you don't understand anything I'm saying, please stop me. I mean, you cannot stop me directly, but you can tell Luca to stop me, and I will just repeat what I said once again, no problem whatsoever.
So if there are no other questions, we can stop here and see you tomorrow morning, everybody, at 10 a.m.
Thank you.
Okay. Thanks again, Pilar. Thanks.